In elementary algebra, completing the square is a technique for converting a quadratic polynomial of the form to the form. In this context, constant means not depending on x. The expression inside the parenthesis is of the former, za plus a constant. Thus, is converted to for some values of h and k. Completing the square is used in solving quadratic equations, graphing quadratic functions, evaluating integrals in calculus, such as Gaussian integrals with a linear term in the exponent, finding Laplace transforms. In mathematics, completing the square is considered a basic algebraic operation, and is often applied without remark in any computation involving quadratic polynomials. Completing the square is also used to derive the quadratic formula. Overview, background. There is a simple formula in elementary algebra for computing the square of a binomial. For example, in any perfect square, the number p is always half the coefficient of x, and the constant term is equal to p2. Basic example, consider the following quadratic polynomial. This quadratic is not a perfect square, since 28 is not the square of 5. However, it is possible to write the original quadratic as the sum of this square and a constant. This is called completing the square. General description, given any monic quadratic, it is possible to form a square that has the same first two terms. This square differs from the original quadratic only in the value of the constant term. Therefore, we can write where k is a constant. This operation is known as completing the square. For example, non-monic case, given a quadratic polynomial of the form, it is possible to factor out the coefficient a, and then complete the square for the resulting monic polynomial. Example. This allows us to write any quadratic polynomial in the form. Formula. The result of completing the square may be written as a formula. For the general case. Specifically, when A equals 1. The matrix case looks very similar. Where has to be symmetric. If is not symmetric, the formulae won't have to be generalized to. Relation to the graph. In analytic geometry, the graph of any quadratic function is a parabola in the xy plane. Given a quadratic polynomial of the form, the numbers h and k may be interpreted as the Cartesian coordinates of the vertex of the parabola. That is, h is the x-coordinate of the axis of symmetry, and k is the minimum value of the quadratic function. One way to see this is to note that the graph of the function e, x, a equals ax2 is a parabola whose vertex is at the origin 0, a0. Therefore, the graph of the function e, za a equals a, za ah2 is a parabola shifted to the right by h whose vertex is at, as shown in the top figure. In contrast, the graph of the function e, x, a plus ak equals ax2 a plus ak is a parabola shifted upward by k whose vertex is at, as shown in the center figure. Combining both horizontal and vertical shifts yields e, za a plus ak equals a, za 2 a plus ak is a parabola shifted to the right by h and upward by k whose vertex is at, as shown in the bottom figure. Solving quadratic equations. Completing the square may be used to solve any quadratic equation. For example, the first step is to complete the square. Next we solve for the squared term. Then either. And therefore. This can be applied to any quadratic equation. When the x2 has a coefficient other than 1, the first step is to divide out the equation by this coefficient. For an example, see the non-monic case below. Irrational and complex roots. Unlike methods involving factoring the equation, which is only reliable if the roots are rational, completing the square will find the roots of a quadratic equation even when those roots are irrational or complex. For example, consider the equation. Completing the square gives so, then either, so. In terse language, equations with complex roots can be handled in the same way. For example, non-monic case, for an equation involving a non-monic quadratic, the first step to solving them is to divide through by the coefficient of x2. For example, other applications, integration, Completing the square may be used to evaluate any integral of the form. Using the basic integrals. For example, consider the integral. Completing the square in the denominator gives. This can now be evaluated by using the substitution way equals a z plus a3, which yields. Complex numbers, consider the expression. Where z and b are complex numbers, z and b are the complex conjugates of z and b, respectively, and c is a real number. Using the identity u2 equals u, we can rewrite this as, which is clearly a real quantity. This is because, as another example, the expression where a, b, c, x, and y are real numbers, with or a0 and bar a0, may be expressed in terms of the square of the absolute value of a complex number. Define. Then. So. Idempotent matrix. A matrix M is idempotent when Ma2 equals M. Idempotent matrices generalize the idempotent properties of 0 and 1. The completion of the square method of addressing the equation showed that the idempotent to a, two matrices are parametrized by a circle in the plane. The matrix will be idempotent provided which, upon completing the square, becomes in the plane. This is the equation of a circle with center and radius 1/2. Geometric perspective. Consider completing the square for the equation. Since x2 represents the area of a square with side of length x, and bx represents the area of a rectangle with sides b and x, the process of completing the square can be viewed as visual manipulation of rectangles. Simple attempts to combine the x2 and the bx rectangles into a larger square result in a missing corner. The term 2 added to each side of the above equation is precisely the area of the missing corner, whence derives the terminology completing the square. 1. A variation on the technique, as conventionally taught, completing the square consists of adding the third term, var 2 to get a square. There are also cases in which one can add the middle term either 2 or a 2 to get a square. Example, the sum of a positive number and its reciprocal, by writing. We show that the sum of a positive number x and its reciprocal is always greater than or equal to 2. The square of a real expression is always greater than or equal to 0, which gives the stated bound. And here we achieve 2 just when x is 1, causing this square to vanish. Example, factoring a simple quartic polynomial. Consider the problem of factoring the polynomial. This is. So the middle term is 2, x2, 18, and equals a36 x2. Thus we get the last line being added merely to follow the convention of decreasing degrees of terms. References. Algebra 1, Glencoe, ISBN 0-07-825083-8, pages 539 €544. Algebra 2, Saxon, ISBN 0-939798-62-X, pages 214 €214, 241 €242, 256 €257, 398 €401. External links, completing the square at planetmath.org. How to complete the square, Education Portal Academy.